Hi there. In today's question, we are looking at question 2, which is from the 2024 November paper 1. All right. So this is a number patterns question, and here we've been told that the first term of an arithmetic series is 7, and the common difference of the sequence is 5, and we're also told that the series contains 20 terms. Okay, so the first question is asking us to calculate the sum of the series. So we know that the sum of the series of an arithmetic sequence is given by Sn is equal to n over 2, open bracket, 2a plus n minus 1d, close the square bracket. Okay, so let's see if we have all the information. We do have n, it's 20 terms. We know a, we've been told it's the first term, which is 7, and we also know the common difference d. So that means we have everything that we need to solve for 2.1.1. So therefore, the sum of 20 terms will be equal to 20 divided by 2, and then for a it's 7 plus 20 minus 1, d is 5. Okay, so putting that in a calculator, you find that your answer will be 1090. Okay, so this was very doable. Okay, let's move on now to 2.1.2. Here we've been told the original arithmetic series is extended to 75 terms. The sum of these 75 is 14,400. Then they said using sigma notation, write down an equation for the sum of the terms added to the original term. So here the focus is on the terms added. So we have the sum of the 75 and we have the sum of the 20. We just calculated it in 2.1.1. So that means the difference between those sums that we have will then allow us to write a sigma notation equation. Okay, so to begin, let us start by getting the difference between the sum of 75 and the sum of 20. So S75 minus S20 will be equal to, I'll write it here. So the sum of 75 terms is 14,400. And for 20, it's what we have. It's the 1090. Okay, so this difference will be 13,310. Okay, so that's the sum of the values from 21 up until 75. The next step is now to set up the sigma notation. So when you write a sigma notation equation, you need the general term. So even though we've added 75 terms, the general term will remain the same. So let's get the general term, and we can use the information that we were given above and then substitute that into our sigma notation. So the general term of an arithmetic sequence, a plus n minus 1 d. So we're just getting the general term. We won't substitute for n. A is 7, and then n minus 1, and d was 5. Okay, now time to simplify. So multiplying the 5 in, so that would be 5n minus 5. Okay, so therefore, now we can just simplify. 7 minus 5 gives you 2, so that means we now have 5n plus 2. And this is our general term. Now we've got all the information we need to set up our sigma notation equation. So this is sigma. Okay, so at the top is the number we're going to substitute last, and for us that will be 75. And at the bottom is the number we substitute first. And because here we already calculated the sum of the 20, that means we start substituting from 21 if you want to determine the sum of the numbers in between. And then our general term, which we have, which is 5n plus 2. And here let's indicate that we are starting at n is equal to 21. And we also know the sum of this. It will be that 13,310 that we calculated at the top. Okay, so just to summarize how we solved this problem, they wanted us to write down an equation for the sum of the terms added to the original series. So we already knew the sum of the first 20 was 1,090. Then they told us the overall sum of all 75, which was 14,400. So we then had to get an equation for the sum of the difference. So that's where we first calculated the difference, which would be 13,300. Then you need your general term using the normal sequence. And then lastly, we substituted all of that so that it can be written as a sigma notation equation. Okay, now moving on to question 2.2. Here we've been told that the sequence of the first differences of a quadratic pattern is 1, 3, 5. And in 2.2.1, they asked if T99 of this quadratic pattern is 9632, calculate the value of T98. Okay, so we need to remember that this is the sequence for the first differences. So the first differences of a quadratic pattern produce an arithmetic sequence. So let's begin with a question 2.2.1. So we have 1, 3, 5, and it continues. These are our first differences. So because we are going to be dealing with the terms in the quadratic sequence and the terms in the first difference sequence, let's rather call these A1 to represent the arithmetic series. So it'll be A1, A2, and A3. So since this is the first differences, we can then produce a general term that will allow us to then be able to determine the difference between two quadratic terms. Okay, so that would be an is equal to a plus n minus 1 multiplied by d. So let's calculate d. It would be a2 minus a1. Here that's 3 minus 1, which is 2. Okay, so for an, it will be 1 plus n minus 1, and then our d is 2. So an will be 1 plus 2n minus 2. Okay, therefore the general term for the arithmetic sequence, which is the first differences, will be 2n minus 1. Okay, now that we have the general term, we need to use this to determine T98. So with the way quadratic sequences are set up, if you have Tn over here, Tn minus 1 over there, this will then be your first difference. And in our scenario, Tn is equal to T99, and here this will be T98. And then for the first difference, we were given the equation An is equal to 2n minus 1. All right, so if we can get this in, we can then subtract it from T99, and then that will allow us to get the value of the 98th term. Okay, so how do we get in for the first differences? Well, it will be the difference that takes the position of the term just before Tn. So for example, the first term in the first difference sequence will be the difference between T2 and T1. So that means this term, this first difference that we're looking at for T99 and T98, it will be the 98th difference, because it's between 99 and 98. It can't be the 99th difference because that will be between T100 and T99. I hope you get the picture. Okay, so now that we know the value of n, we can actually substitute it and then solve for T98. All right, so we're looking for A198, which is the 98th position. Let's just erase that, A98. Okay, so that will be 298 minus 1, which will be equal to 195. Okay, so now we know that T98 will be equal to T99 minus that 195, which is the difference between the two terms. And T99, we were told it's 9,632. And minus 195. So therefore, T98 will be 9,437. And that's our final solution. Okay, moving on to the last question, 2.2.2. We are told if it is further given that the third term of the quadratic pattern is 32, determine the general term Tn of the quadratic pattern. Okay, so this is a typical quadratic pattern equation where we need to determine how to get the general term. So let us do that. So we have T1, T2, T3, and T4, which we don't know. But we know the differences between them, which is the first differences we've been working with. This is 1, 3, and 5. And then the second differences are 2. Okay, so to get our general term, we know the general equation is an squared plus bn plus c. Okay, let's get a. So a will be given through calculating 2a, and that's equal to the second differences, which is 2. And dividing both sides by 2, we find that a is equal to 1. For b, it's 3a plus b, that's equal to, let me highlight them. So now we are looking at our first difference, and it will be equal to 1. So 3a plus b, a we now know to be 1. Okay, so this is therefore b is equals to negative 2. And then lastly, we've got a plus b plus c, which will be equal to term 1. Okay, so we were told that term 3 is 32, so we can work backwards to determine those values. So over here, if we've got 32, that means minus 3, you get 29. And then minus 1, you get 28. That means here it will be 28. And we can proceed with our calculation. A is 1, B is -2, and we're trying to solve for C. So 1 minus 2, that's -1 plus C being 28. Therefore, C is 29. Okay, now we've got everything, so now we can get our general term. So therefore, Tn for this quadratic pattern will be n squared plus, well, it's -2, so then it becomes minus 2n plus 29. And that's it for this question. Now, let's move on to question 3. So here we are told that a circle with a radius of 6 centimeters, let's change that color, is drawn, and a second smaller circle is drawn through the center of the first circle and also touches the first circle internally. A third smaller circle is drawn through the center of the second circle and touches the second circle internally. The process of drawing circles continues to form a geometric pattern, also known as a geometric sequence. Okay, now let's look at question 3.1. They said write down the radius of the third circle. All right, so 3.1. So the radius of circle 1, I'll call it R1, was equal to 6 centimeters, right? So looking at our circle, that will be from here, the center of the big circle, all the way to the circumference. This is the 6 centimeters. And then we see that this 6 centimeters, this R1, is actually the diameter of this second circle from there to there. And then the smaller circle, we see that the radius of the second circle is the diameter of that one. So let's pick a different color, like a purple. So I don't know if that is visible. So what we can see is that the radius will be the half of the previous radius. So that means over here, for R2, the radius will be half of that one. So that would be 6 divided by 2, which is 3 centimeters. And the third radius will then be the 3 centimeters divided by 2, which will be 1,5 centimeters. So that is the pattern. Let me write this more visibly because that 3 is looking funky. Okay. Now we can move on to question 3.2. They asked us to calculate the sum of the areas of the first 10 circles. So here we're seeing sum and 10 circles. So this is hinting that we are actually looking at a geometric series. So let us then produce the geometric series for the 10 circles. So the area of one circle will be pi r squared, right? So a circle is equals to pi r squared. So for us to create the sequence of the circles, we'll just replace r with the actual radius. So the first one would be pi, and then r over there was 6 squared. The second one will be pi 3 squared. The third term would be pi 1,5 squared, and so on. Okay, so simplifying this, we get 36 pi, and this will be 9 pi, And lastly, 1.5 squared is 9 over 4 pi dot dot dot. All right, so now that we have created our sequence, which we're going to use to reproduce the series, let us now get the key things that we need. So we need R. So R will be equal to Tn over Tn minus 1. We can use T2 and T1. And for us, that would be 9 pi over 36 pi. And that should be 1 over 4. Okay, and then A is just equal to our first term, which is 36 pi. And this is all the information that we need for us to then get our geometric series. So Sn is equals to A r to the power of n minus 1, all divided by r minus 1. Okay, and we are calculating S10. So A is 36 pi, R is 1 over 4 to the power of 10 divided by 1 over 4 minus 1. And we find that putting this in a calculator, you get about, so therefore S10 will be 150,80. So this is the sum of 10 circles, the sum of the areas of 10 circles. Okay, pretty straightforward. All right, let's now move on to question 3.3, where they asked us which circle has a diameter of 3 over 128 centimeters. So we need to recall that our circles, the pattern is based on the radiuses. So if we're looking for a circle that has that diameter, we first need to determine what is the actual radius before we then proceed to determine the diameter. Okay, so that was 3.3. So the radius, let me write radius so that we don't confuse it with r. Radius will be equal to 3 over 128 divided by 2. And this should give you 3 over 256. Okay, so now that we have this, we need to get our general term for the geometric sequence of the radiuses of the circle and not the areas, because previously here we were focusing on the areas. Okay, so Tn is equals to ARN minus 1. That is the general term for geometric sequences. Okay, so what we are looking for in this question is the value of n, because that is what we don't have. A, we do have, it's 6, and then we can determine r. So let me write in a different color. So geometric sequence for radiuses, it's radii. There's no such thing as radiuses. Okay, so The first one was 6, second one was 3, third one was 1,5, and that's how the pattern went. So we can see that therefore A is equal to 6, and we need to get R, which we can say we can use 3 and 6. So T2 over T1, which is a half. Okay, so now we've got our A and we've got our R. We can then substitute into the general term equation and solve for the unknown radius. Well, the unknown position of that radius. So 3 over, let's go back to our blue, 3 over 256 will be equal to 6. R is 1 over 2 n minus 1. So we can divide both sides by 6 just to get rid of that. And then we'll end up with 1 over 512 on the left. And here we will just have a half to the power of n minus 1. Now, when you reach this point, there are two methods to go about it. You can either solve it using exponents, try to get the same bases, or alternatively, you can apply logs. So because we are preparing for exams, this is a good opportunity for us to apply logs. So you know when to apply logs if your unknown is in the exponent. We're trying to solve for n, which is in the exponent, so that means we need to use logs. Okay, so when you apply logs, your unknown is what you write as the subject of the formula. For us, that's n minus 1. And it would be equal to log the base of the exponent, which is a half, and then the log answer, which was 1 over 512. This is what we put in the calculator. And then from this, we get n minus 1 will be equal to 9. And then taking 1 to the other side, we therefore have n is equal to 10. What a coincidence. So that is the final answer for this question.